It's possible to combine both seasonal autoregressions and seasonal moving averages into a single model. This model, of course, was known as a seasonal ARMA model. So seasonal ARMA model, instead of having two parameters, P and Q, like we saw in a standard ARMA model, it now has four parameters. The four parameters, of course, are P and Q from the time series frequency, the time series lags, and PS and QS, which correspond to the seasonal lags. For example, a seasonal ARMA model 1-1 cross 1-1, that is one lag of each the AR and the MA in the time domain, and one lag in the seasonal domain, will have the one lags there. It'll also, of course, have the seasonal lags of both. And of course, if we wrote out this model, it would be fairly complex, but we can take a look at what it would become. So from the seasonal lags, from the AR bit, we'd have xt equals, I didn't include a constant, but we could go ahead and throw a constant in because we normally have something like that, phi naught plus phi 1, xt minus 1, plus phi m, xt minus m, minus phi 1, phi m, xt minus m minus 1. That was the term we saw from the AR. In the MA, we then will have theta 1, epsilon t minus 1, plus theta m, epsilon t minus m, plus, again, a cross product, theta 1, theta m, epsilon t minus m minus 1. And then finally, we have the usual error in the model. So very quickly, it's possible for seasonal ARMA models, especially when you have seasonality in both the AR and the MA, to become heavily parameterized, which may not be desirable in forecasting situations. I mentioned previously, but it's fairly rare as well to include seasonal moving average terms, or in fact maybe moving average terms at all, for two reasons. One, you can capture them with ARs, usually in most cases, unless the theta is very, very close to 1. Second, they complicate the estimation in that instead of simply relying on OLS, you now have to use maximum likelihood or nonlinear least squares or a non-deterministic optimizer, which may not be ideal in the sense it will slow down the ability to generate forecasts, and certainly in the forecasting competitions, which we're sort of based our course on, this is an issue because you have to make so many forecasts across so many series and so many horizons. Finally, we can put everything together into a single class of models. These models are known as seasonal autoregressive integrated moving average models, or SARIMA. SARIMA models add an additional set of parameters to the parameters we saw before. So we have the same P and Q and the same PS and the QS, but what's new is we have two parameters, D and DS, and the D stand for differencing. So in addition to having autoregressive moving average orders, the model itself also integrates the differencing parameter as part of the specification. So the D or DS tell how many times we've differenced it. So obviously the D is for standard differencing. That is, when we have D, we would have delta xt. If we have DS, we would have delta m of xt. That is, we'd be modeling the series with a seasonal difference. In practice, these are both either set to 0 or possibly one is set to 1 and the other is set to 0. In principle, there's no limit to how you could configure this model, although empirically it's not usually necessary to have more than one difference, and usually you wouldn't want to have in particular a difference at both the time series and the seasonal frequency. Just to understand how differencing operates, in fact, it's very simple. In particular, if you have a, say, SARIMA P1Q cross PS0QS, then if we simply took the regular first order difference, then this just gets rid of the D operator and the rest of the parameters of the model would stay the same. Because of course all we've done is we've taken the difference and once we've applied the difference to xt, there's no more differencing needed. Similarly, if you have a seasonal difference, so in the second line here we see we have PS1QS, then if I took delta m xt, as I take the seasonal difference of m, And again, I simply get rid of the need for the seasonal differencing. And so the integrated order in the SARMA model is just a convenient tool that allows us to track this as part of the model specification. It, of course, will help us generate forecasts in a sort of automated way because we don't have to worry about whether it was differenced or not. But in practice, there isn't a huge difference in terms of tracking it other than just some convenience. When we have difference models we want to forecast, we need to think a little bit about how we forecast these. So forecasting these, again, is not particularly challenging, but of course the important thing to think about is now we're forecasting the difference. So the model we actually have, this is particularly the case where d equals 1, the model we have is a model for the changes in xt. So when I want to get the one step ahead forecast, we simply use the fact that the one step ahead forecast by definition is going to be xt plus delta xt plus 1. Very mechanically, we can see that delta xt plus 1 is xt plus 1 minus xt. And then if I add in xt, clearly I get what I want. So this is a simple thing. Obviously, if I want to do two step ahead or further steps ahead, I need to sum up all of the forecasts back onto my original series. And so we'll see that when we actually get some of the forecasting methods. But it sort of also helps us understand what's going to happen when we look at prediction intervals. Prediction intervals are not particularly challenging here as well. They're also going to depend on the sort of MA infinity representation. Now they're going to depend on the MA infinity representation of the differenced series. So they're going to depend on the MA infinity representation of the sort of series that once we've differenced it to make it stationary. So they're going to have the usual form, that is the forecast, in particular, should be a sort of plus minus here, plus minus 1.96, and now I have this other alternative version of the standard deviation. To understand what the standard deviation is here, it's going to depend on the variance of the residual. So the variance of the forecast error at horizon h depends on the variance of the residual, and then it's going to have a double sum here. So we see it depends on accumulating all of the shocks up to period h from 1 to h, and then we're going to have this other sum here, whereas we have to take 1. So it's going to take the sum of 1 plus all of the impulses from j, and now I just see there's a little small error here. This should not be h minus 1. It should be I, because we need to do it for each of the i's. So for one of the i's, we're just going to have 1. For another of the i's, we're going to have 1 plus xi1. For the next one, we'll have 1 plus xi1 plus xi2, and so on. And then we square these terms here. And so we square these terms here. And this is just comes from a careful accounting of all of the shocks that are ultimately going to appear when we think about summing these differences up across multiple horizons. So to understand, just a little bit about what these might look like, in the case of a very simple SARMA 110 with no seasonal components, so that's just an AR1 but in differences. When I want to actually look at the error variance, I'm going to have 1 squared, that's from the first one, 1 plus phi squared. There would be another term here, which would be 1 plus phi squared, and the last one would be 1 plus the sum of phi from powers 1 through h minus 1, all squared. And so this in the end is just the variance we get for this particular model of the forecast horizon, of the forecast intervals, of the forecast errors, keeping so this is just what's going to show up in the variance of the forecast errors once we keep careful track of the fact that we're accumulating the forecast errors across multiple periods. Because when we difference the series, we are in practice assuming that the series is non-stationary or first-order integrated. What we see here is that the longer we go out in time, the wider these confidence intervals will become. This is simply something that's an artifact of the choice of differencing, which reflects the fact that this model assumes that we have a unit root or a random walk. Forecasting from a seasonally differenced model is not fundamentally different, so when we want to do the one step ahead forecast, instead of starting at the final value of xt, we need to go back m periods from the value we're trying to forecast. We then add to that the change between that period and the forecast horizon. In particular, we see that this delta here is xt plus 1 minus xt plus 1 minus m. Of course, we have the conditional expectation given time t. Well, that's known at time t, so in fact it's going to be the same as this value. So when we rearrange, we simply get that term as 0, and it drops out, and we get what we want. But it's important to realize that this sort of conditional expectation of delta the conditional expectation of delta m, that is the seasonal difference of xt plus 1, that's exactly what's on the left-hand side of our model. And so that's the natural thing to forecast. The really key insight here is that we don't add the final value of xt, but in fact we have to go back m periods from the final value. So this, of course, works for every horizon. So again, you always start from that same initial value, and then you simply accumulate up all of these different forecast horizons, and that will give you what we need. Finally, we can put everything together to build a coherent model that can account for a really, really wide range of things. So when we put everything together, the first thing we'll want to consider is whether we need a constant in the model. It's pretty standard to include a constant in the model unless you have a really, really strong knowledge a priori that the series should be mean 0. But then serious questions arise. Do I need a trend in the model? So often we might want to say test for the trend or have some way to determine whether we have a trend. Do we want seasonal dummies in the model? That's something you might also want to consider. Do we need an autoregressive or a seasonal autoregressive term? And then somewhat more rarely, you might want to consider a moving average or a seasonal moving average. Although again, the reason why these are rare is that they just make the estimation a lot more difficult. It's very easy to have a model that includes any or all of the terms in blue using only OLS. And of course I say seasonal dummies, but this of course could also be Fourier terms as well, or in addition to those. So a few recommendations that have come out of the literature for forecasting when you're thinking about this class of models is that the really key choices turn out to be whether you difference the series or not, how you use trends and seasonal dummies. Because over moderate horizons, not just one step ahead, but once you look at sort of, say 5 or 10 or even 2 years ahead with monthly data, 24 periods, that almost all of the forecast is going to come from things like the trends and the seasonal dummies. The autoregressive components should be more or less run out by then. And so it's really going to play a key role as to the choices you make there. It's not to say the ARMA terms don't matter. They matter usually for shorter horizons. But once you do long horizon forecasts, they're going to be less important. And the final thing I mentioned, differencing, is the rule of thumb for forecasting is you always want a difference if you're close to a unit root. Obviously, you can use an augmented Dickey-Fuller test or some other unit root test to test for a unit root, but the rule of thumb says even if you're sort of close to a unit root, that is, you don't even need to have an exact test. If you're close to a unit root, that is, you estimate a root that's, say, 0.9 or 0.95 or sometimes even less, then you might want a difference and estimate your model in differences. In conclusions, ARMA brings a unified framework that allows us to model trends, seasonal, and cyclical components. The key things when we're actually building models for forecasting are going to be the choice of differencing, trend, and seasonal specifications. These matter a lot over longer horizons. One thing I haven't actually mentioned on the slide, but also important, is whether you should use xt versus the natural log of xt. So the choice of levels or logs plays an important role. Rule of thumb here is that when xt is strictly positive, you probably want to use the log of xt. Obviously, you're making an assumption that xt is fundamentally strictly positive. In many cases, we'll have expert knowledge that lets us know that xt, say, it's a price or something like a price, and so it must always be positive. And so it's good to enforce that if it's true. Obviously, if you use the log of xt, you need to transform it back. We've talked about various methods and other lessons of how we do that using the exponential function or assuming log normality. Forecasts of differences were seen to accumulate the difference forecasts. So in principle, they're very straightforward to produce. And the prediction intervals also have to reflect this additional accumulation. And prediction intervals, when you difference data, will tend to get wider as the horizon grows.